sum of what we know flowed through each one. So if we add those two, 12 plus 6, that's 18 amps. That's a lot of current. That is by far the most current we've seen in the hookup of these resistors with this battery. Those resistors did not even have that much current when they were placed in there by themselves. We got 12 amps and 6 amps, but now we have a tremendously large total current. And if I total is so large, what does that mean about the equivalent resistance of this entire circuit? It's very small. There must be very little resistance in the circuit if the current flow is such a huge gushing of charge. Okay? So there's something about hooking up resistors in parallel that makes it so that resistance is actually very low. Let's figure that out. So first, let's actually use this equation symbolically as a jumping off point by just plugging in Ohm's law for the individual resistors over here and then Ohm's law for the entire circuit over here. So here we can plug in, of course, the total current that will flow will be dictated by the battery voltage and the equivalent resistance in the way. That's just this equation right here, flipped for the total current. And then here's the Ohm's law for each of them individually. And then, of course, I realized that these are all the same voltage. And so I now find what my addition rule is for resistors in parallel. It's a 1/over rule. This, by the way, works however many you have. So it's a strange rule where you have to take the reciprocals of the resistors, add those, and then you'll get the reciprocal of the equivalent resistance. And hopefully from math class you should understand that this cannot just be flipped into this, okay? So on your calculator, this is what you might do. You have a 1/over button on your calculator. That's how I use it. It's a -1 button. So type in your resistor. So that's 1 ohm, right? Then hit inverse. Plus 2 ohm inverse. And then don't forget what you have just achieved when you hit equals is not the equivalent resistance, it's 1/over that. So you have to flip the answer as well. Okay? So in this case, if you did that, you'd have 1 plus 1/2. That's 3 halves. But 3 halves is the 1/over the resistance, so the equivalent resistance is 2/3. And I want to point out that I took a 1 ohm resistor and a 2 ohm resistor, but when I combine them in this way, their overall resistance is 2/3 ohms, which is less than either one of those is by themselves. So let me finish off my chart here. The addition rule for parallel resistors is a 1/over rule. And when you get your result, that result is actually smaller than any of the individual resistors. Okay? While we're at it, before I forget, let's figure out what would happen if I had a bunch of identical resistors. What would happen if I had 1/R equivalent plus 1/R, 1/R plus dot, dot, dot? If I had n of these for n resistors, then this quantity would become n times 1/R. And when I flip that, I'd actually find that I had to divide by the number I had. So the equivalent resistance here is going to be that for n identical resistors of value R, you divide by R. Again, an extremely handy shortcut if you happen to get lucky enough that all your resistors are identical. So for instance, let's stay for a second there on the identical resistors bit. Let's say I had a box of 10 ohm resistors, or actually let's do I don't know, what's a good value to do? Let's do, I had a box of 100 ohm resistors, and I had 20 of them. All right. If I put them all in series, my equivalent resistance would be what? If I put them in series, 2,000. I'd have 20 100 ohm resistors in a row. That'd be 20 times 100. That's 2,000. But if I put them all in parallel, what would be the equivalent resistance of 20 100 ohm resistors in parallel? 5. 100 divided by 20. Okay. So I guess before I even forget, let's make sure that this indeed does reproduce the results that I already know. If I go ahead and I put that into my Ohm's law equation here, if I have a 12-volt battery and I attach it to a circuit with an effective or equivalent resistance of 2/3 ohms, I can use this to calculate my total current that would be drawn, and this is indeed going to corroborate my previous answer, which of course it did, because I just basically did the same thing, one with numbers and one with symbols, okay, and then plugged in the numbers at the end. So we do indeed have a very large current here because we have a very small resistance. So the final thing I'd like to do, some of you may be wondering, this just seems weird. How can I add more and more resistance to a circuit and the resistance doesn't get higher, it gets lower? So here's my best analogy for this. Instead of resistances here, let's imagine that these are toll booths on the Bay Bridge. Okay? Toll booths are in parallel, right? If you drive across the Bay Bridge and you manage to drive through two toll booths, you probably have the police after you because you did something really illegal. You pick one and you go through that. Yes? You have options. So in terms of the resistances, well, this is easy to go through. So this is like fast track or a really fast, someone that makes change really fast or something like that. And then this might be a larger resistance. That's like somebody that takes forever to count out the change, right? They don't have that little wad ready to hand you. They're like, start counting it when you get there, right? So here's the thing. You might say that this second option, this larger resistance option, it's worse thing, but it's still better to have them there than not, right? So if you just had this lane, no matter how fast that lane was, it's still better when they open up another lane. Even if that other lane is slower, some cars can still go through that way. That's why they have them all open when you have the most traffic expected, right? So a 1 ohm resistor, any other parallel branch, no matter how resistive it still makes it overall easier to go through. It lowers the resistance. If you added a third resistor in here that was 1,000 ohms, well, that's just an extra option. Very few will take it, but it's still better to have it there than not. So adding another resistance in parallel is going to just make the resistance go down further. Okay? Every branch that you add in parallel is going to lower the total resistance of the circuit because it's another branch that you didn't have before. Nobody could take it before, and now this new branch, no matter how much resistance it might have on its own, is still an extra option that nobody had before. Okay? Does that make sense? That's why every resistance that you add in parallel lowers the resistance. Okay. So now I think we've gone ahead and gotten all our numbers. We have some point of reference, and I want to, of course, go back and compare it here so that I can hook up this demo and we can see if the results are as expected. So let's find some room here. So here's our predictions, our demo predictions. So to give us the same flavor to both predictions, I'm going to look at, okay, how does each individual bulb do relative to when it was connected alone? And then how do the two bulbs compare connected to each other? So the only thing we have access to, because I don't have a voltmeter, anything to measure voltage or current, is power, right? And we look at that with brightness-wise. So here is our 1 ohm connected by itself, 144 watts. Here it is connected in parallel, 144 watts. This was 72 watts alone. Now this is 72 watts in a parallel. So that's one thing we're expecting, is that each bulb actually has the same brightness when connected alone. So that's one thing we're going to look out for. And in a relative comparison, we are indeed expecting that the larger, or I guess let's put it as, yeah, we'll put it as like it's in the chart. So the larger resistance dissipates less power. So the larger resistance should be less power, so less bright. So that's what we're on the lookout for. Let's do it. So I have the same bulbs as last time. They aren't literally 1 ohm and 2 ohms, but they're in that same ratio, so R and 2R. Let's quickly connect them alone so that we can remind ourselves what their brightness was when connected alone. So get a mental snapshot of this guy. That's that resistor. Get a sense of how blindingly bright that is. And then we'll connect the other one, like so. Get a snapshot of how bright you think that is. And then let's connect them in parallel. So we're going to have our higher voltage equipotential over here and our lower voltage equipotential here, and we'll give options to go between them. You can go through one or the other, not both, but one or the other. So we connect these up, like so, and we see them like this. So hopefully you believe me that each of them maintains the same brightness when connected alone or with the other one. If you want, I can disconnect one. You can watch the other and see that it doesn't change at all, right? So no change to the other one, whether this one's connected or not. Yes? You didn't see it because of my hand. I'll do it again. So whether I connect this or not, it has no effect at all on the other one. Yes? Okay? And hopefully, this is now head-to-head, hopefully you can see that we're expecting that the larger resistor has less power, so that's the bottom one there. Hopefully you believe me that while also still quite blinding, it's slightly less blinding, okay? For instance, you can see the filament a little bit in this one. This one is just too overpowering, okay? So our predictions of parallel circuits has hopefully been seen here. So here's what's going on. It may be surprising to you that each bulb has the same brightness when connected alone as when connected with others. But that's what the hallmark is of a pure parallel circuit, is that each is its own parallel thing that's doing its own thing regardless of whether there are other things there. Remember, each of these bulbs has full access to the entire voltage drop of the battery, 12 volts, whether or not there are any others that are also partaking of that. So each bulb has the same has its resistance, it has the same voltage, and it's going to have the same current and power. Everything's the same for a bulb, whether it's connected alone or connected with others. Okay? Each of them are truly independent branches. Okay? There are independent branches. Everything that's going on with each branch is the same, whether it's one branch only or one branch of 1,000. Okay? In a perfect parallel circuit, that's what happens. Now, I'm not saying that the total resistance is the same. Every time I add a parallel branch, okay, I am making the circuit easier to move through. I'm opening another lane on the toll plaza. So every time I add another one, I'm making the circuit overall, as a whole, easier to move through. And if the total resistance goes down, what happens to the total current? It goes way up. I would not want to put my hand here right now, because the total current that's needed to service all three of these is very high. However, because the total or equivalent resistance went way down and the total current went up, how is it that the branches that were already there didn't see more current? Well, of course, they're doing their thing. The increase in total current just went to service the new branch. So what we have here is that each resistor that is added, the total resistance goes down, the total current goes up, but the new current just services the new current just goes to the new branch. The other branches still receive as much or as little current as they were getting before. They're independent. They all pull, each branch pulls as much current as it wants, based on the fact that it has access independently to the entire voltage drop given by the battery. Okay? Does that make sense? Question?
Yeah, I was just wondering, in the beginning though, you were saying when you said when you hooked up both resistors that the power did dissipate slightly, even though we couldn't tell. I guess I was confused as far as, do they totally stay the same?
Did you see that?
No.
I said that. Yeah. Oh, yeah. Well, here's why. The pure parallel is a myth. You can't have true parallel. This here has resistance, right? And so here's the problem. I'm making this section of circuit easier to move through, right? So what's going to happen here, that's a good example of what I was talking about earlier today. I was going to bring this up later, but this is a good time as any. So what's happened is that I have really, this is the part that you can see. But this itself, the wire itself has resistance. And so what happens is if I have R1 and R2, what I'm doing here is I'm decreasing R2, and that's actually going to decrease the voltage drop across that section. So this voltage is, these don't really have access to the battery voltage directly. This is going to decrease because more of the voltage drop is going to happen across the wire. So at some point, if I added 50 resistors here, this wire would start to get hot because I have so much current. We're talking here 18 amps. 18 amps, that's no joke. So at some point, even the wiring itself, the resistance matters. So what you're going to see is that in lab, you're not going to have one of these guys. You're going to have some cheapo type thing, and you'll notice that if you start hooking up 3, 4, 5 things in parallel across it, they all dim. That's because you're having voltage drop across the wire itself. So I'll get into that. I was going to wait a little bit for that, so I'll bring that up again. But that's totally true. That's why, by the way, I'm using this thing. Okay, this thing is built to put out 350 amps. Okay, so that's something that if you're going to output that much current, you better make sure that all your accessories connecting it have very, very low resistance. These are very, very thick. You can see how thick this is. That's to make it very low resistance. Okay, so that makes it so that when I'm hooking these guys up, you don't see this huge plunge in brightness. Because then someone says, well, you said it should stay the same. Well, it should stay the same in perfect conditions. This is as close to perfect conditions as I can supply. Okay, but that's where we're going with this. What we're going to is realizing that circuits are going to have different parts of each of these. It might have a parallel section, but that parallel section might be in series with another section. Okay, so we're going to have to take all of these ideas and kind of incorporate them together. So these might be in parallel, yes, and every branch I might add here makes it lower resistance. But if I'm lowering this section, I'm also lowering the amount of voltage drop that will be taken by this and increasing it over here in the series section. And this is jumping the gun a little bit, but I was just kind of wanting to address your question. Does that make any sense? Or I'll come back to that and I'll go over it in some more detail. Okay, so we have the series and parallel all taken care of. This is just pure series and pure parallel. So again, we have Which one is the same and which one is not for current voltage is reversed. We have the addition rules are a little different. And then the big resistors get all the action, then the bottlenecks on the series, and then the sideshow where they get the less stuff on the parallel. So before I go ahead and just knock out some massive combo circuit and the computation, I want to take a little bit of a breather and talk concepts. So you'll notice these kind of problems also all over your homework. There's not anything you have to compute per se, but just understanding what kind of what increases, what decreases, things like that. So let's take a look at a quick couple conceptual examples. I'll do a couple of these. Let's do one like this first. No, let's not do one like that first. Let's put one here. Something like that. So I have R1, R2, R3. I have a switch, and the switch can of course be connected or disconnected. It can be open or closed. Right now it's in the open position. So let's ask what happens to, when we close the switch, what happens to, I guess let's do all the fun. It's R1, R2, R3, I1, I2, I3, V1, V2, V3. What happens to them? Do they increase, decrease, or stay the same? Okay, so first of all, easy first line, resistance is intrinsic, so you can't change the resistance unless you change the physical properties of something. So these are always constant, these are intrinsic. That's easy. I rarely ask you that one because that's kind of just a gimme. For I3, hopefully it is obvious that there will be no current through R3 to begin with because there's no viable path through there. It's not like charges flow through here and then, oh, that's a dead end. I guess we shouldn't have done that. They know, okay? So obviously, I3 is going to increase from 0 when you close the switch. It wasn't getting anything. Okay, how about the current through each individual resistor? What happens to those when you close it? What's that? The same, exactly. So these are two independent branches. They're doing their own thing, right? They have the same voltage drop regardless. They have the same resistance, so they're completely the same. These guys stay the same. But if I1 and I2, the current requested by those two resistors stay the same because they're doing their own thing independently. But I3 increases, of course, the sum of those is the total current. Of course, the total current we can say increases. And the total current we can say increases because the overall resistance of the circuit decreases. By adding a third lane, so to speak, we made the circuit easier to move through and the total current will be larger. Of course, that increase in total current just goes to servicing the newly opened branch. Okay? What about the voltage drop? What happens to the voltage drop across the first two resistors? It's the same. They have access to the full voltage drop. Now, for V3, of course, it didn't have any current going through it, so it must not have been offering any kind of reward. In fact, this was all an equipotential at the beginning. That whole thing was at the same voltage. And so that's why why would something flow through R3 just to get to the same voltage as it had before? So now when we close the switch, this increases from 0. That is what takes, I guess I can draw it here, when this gets closed up, it makes this part be part of the higher voltage equipotential, and it makes this all part of the lower voltage equipotential. So now we've created a motivation for charges to go through R3. So remember, as goes V3, so goes I3. When this starts to be something, then the current will flow accordingly. Current doesn't flow for nothing. It flows because it has a motivation. All right. So that's a simple problem. That's really just having a parallel circuit where we add in an extra branch. We acknowledge that the total resistance or equivalent resistance goes down with the addition of a third branch, and the total current goes up. But really, the first two branches, it's the same as business as usual. Let's go ahead and do another example like that. Oh, and I forgot to mention too, hopefully now understanding series and parallel, you start to see that they both have their advantages and disadvantages. For example, are your car headlights, are they wired in series or parallel?